Hello again. In this section we're going to talk about interpretations of the derivative, higher derivatives, and differentiability. So let's start off by talking about some of the interpretations. And the place to start is how we developed the concept of the derivative. And that was as the slope of the tangent to a curve at a point. So if we think of that interpretation, it can give us a good idea of what we mean by the derivative of a function at a point. So for example, here's a curve that I took from one of the Paul's online notes pages. And so here we have this curve, and we're asked to use the graph of the function f of x to estimate the value of each expression. All right, so first we're asked to evaluate f prime at -5. So again, this means the derivative of the function at -5. All right, so at -5, we see that the curve passes through the point -5, -2. So from algebra, that means that f of -5 is -2. But that's not what we were asked for. We were asked for the derivative of f at -5. So here we have to, in a sense, think of the interpretation. What's the slope of the curve at that point? And so one way to do this would be to try and draw a tangent line to the curve at this point. And this is going to be difficult for me to do using the tablet device that I have here, but I'm going to try and do this. Let's see, maybe it looks like this. There's a tangent line. And again, so maybe that's what the tangent line looks like at that to the curve at that point. And so then all we have to do is ask ourselves, what's the slope of the curve at that point? What's the slope of the tangent line? And this is really just an algebra idea. Let's see, from this point we find another nice point on that line, and so it looks like it has a rise of 3 and a run of 1, and it's certainly a positive slope because it's increasing from left to right. It's rising from left to right. And so I might estimate that f prime at -5 is 3. Why don't you try the next one? Estimate f prime at 1. Alright, so at 1, here's the point on the curve. F of 1 is 4, but that's not what we were asked for. We were asked for the tangent, right? The slope at that. So if I was to draw this line, maybe it's tough. Maybe it looks like that. And so then that line has a negative slope. It's falling. It's going down 1 and right 1. So I'm going to estimate that f prime at 1 is -1. Alright, so now let's answer a few other questions that's going to lead us to something important. Over what intervals is the curve increasing? Alright, and so increasing means, if you remember from algebra, if we go from left to right, is it moving up from left to right? That's the simplest way to think of increasing. We'll have a better definition of increasing later on in the course. But what does it mean for the curve to be increasing? Is it just moving upwards as we go from left to right? So it looks like it's moving upward until we get to about here. Right? It looks like it changes at about there. So what I would say is where's the curve increasing? I would answer that as the interval from -infinity, assuming the curve continues on to the left, from -infinity to -0.5. Where's the curve decreasing? Well, if we assume it continues on, and as we can see, it looks like the curve is decreasing over the interval -0.5 to infinity. All right, so here's what I'm saying. Over this interval, this is where the curve is increasing. And here's where the curve is decreasing. That's what I'm saying with that interval notation. Are there any x values where the curve is not increasing or decreasing? Well, it looks like the curve is not changing when x is that value, that negative 0.5. And what I'd like for you to notice here is that at that point on the curve where x is negative 0.5, if we look at that point on the curve, if we were to draw the tangent line to that curve, to the curve at that point, notice the tangent line would be horizontal. And that's important. Okay, so now let's look at these intervals. See how the curve was increasing over a specific interval. If we were to think about the tangent lines, let's think of the tangent lines over that first interval, from negative infinity to negative 0.5. If we were to think about the tangent lines, notice that the tangent lines would all have positive slope over that interval. Now, let's consider the second interval that we discussed, where the curve was decreasing. And notice that if I was to draw tangent lines over that interval, notice that all the tangent lines would have negative slopes. That's not a coincidence. That's actually an important concept that we will prove later on in the course. But here's something important. Over what intervals is the curve increasing? If the curve is increasing, if the function is increasing, the derivative, the slopes, the derivative is positive over that interval. Over what intervals is the curve decreasing? If the curve is decreasing, the derivative is negative over that interval. Any x values where the curve was not increasing or decreasing. Let's go back. Let me draw that line back in. And when x was negative 0.5, if we were to draw the tangent line, that tangent line is horizontal. What's the slope of a horizontal line? 0. The derivative is 0 at that point. That's an important concept. So, and we're not going to prove this yet. We'll prove it later on in the course. But here's a big concept that we need to be aware of. If a function is increasing, its derivative is positive. And that turns out to work vice versa. If the derivative is positive, the function is increasing. If the function is decreasing, the derivative is negative, and vice versa. If the derivative is negative, the function is decreasing. And then we have what we'll call, for now, stationary points. Here, when x is negative 0.5, we have a stationary point, a point where the curve is not increasing nor decreasing, and the slope is 0. The derivative of the curve is 0 at that point. This is a big, important concept. So now let's see how we can use these ideas to help us with something. So here we're given the graph of a function. This is the function f of x. Use this to sketch the graph of the derivative, f prime of x. So here we have f of x is given in red, right? F of x is in red. And I will draw a curve. I will draw the derivative in blue. Okay, so the derivative is the slope of the function at the point. All right, so let's think about these points. Let's look at these points. Let's look at these points on the curve. What's the slope of the curve on these points? Well, we can see it's linear, right? The curve is a linear piece there. And let's see, we can easily calculate the slope. Let's see, that's down 1, 2, 3, 4, 5, over 1, 2, 3. Negative 5/3. So over this first interval, right, so over the first interval, the slope is negative 5/3. All right, so what that means is over the first interval from negative 6, where x is from negative 6 to negative 3, the derivative is negative 5/3. I'm going to draw a linear segment right here at the value negative 5/3. Now let's look at the second interval. Over the second interval, the slope is, let's see, it's going up 1, 2, 3, 4, 5, 6, 7 over 2. The slope is positive 7/2. So over that interval from -3 to -1, the slope, the derivative, is 7/2. That's 3.5. So there. Now, over the third interval, the third piece, now the slope is, well, hey, we've got a horizontal line, and we know that a horizontal line has slope 0. So over that third interval, I will draw the curve, the derivative at 0, and I drew it a little bit above just so we could distinguish from the x-axis. And then finally, let's take a look at the fourth interval. The fourth interval, let's see, the slope is down 1, 2, 3, 4 over 1, 2, 3. The fourth interval, the slope is negative 4/3. So therefore, the derivative would be at negative 4/3 over that interval. And so there in blue is a graph of the derivative function from what we can tell. And so we can draw if we're given a function, the graph of a function, we can draw its derivative without knowing a formula, just by looking at the slopes of the curve at various points and looking for some key features. Let's see a more complicated example. So here, instead of linear pieces, here we're given an actual, more of a curve. And so here's what I'm going to do. I'm going to sort of break this up into a few chunks. And I'm looking for some specific features. If we go back to our first slide, I brought up some really important ideas. I said, over where is the curve increasing? And we said, okay, well, the derivative is positive over that interval. Decreasing, the derivative is negative. Not increasing or decreasing, the derivative is 0. Let's use that. And what I'm going to do first is I'm going to try and find any places where the derivative is 0 first. So let's see, where is the derivative 0 first? Well, if we look on the curve, it looks like I've got a stationary point here where x is -1. And it looks like I've got a stationary point here where x is 3. That means that the derivative, again, I'll draw the derivative in blue. That means that the derivative must be 0 at those x values. So I know I have a 0 when x is -1, and I have a 0 when x is 3. Okay, for the derivative, I have a 0 of the derivative when x is -1, and a 0 of the derivative when x is 3. Now let's look at the rest of the curve. Alright, so from -2 to -1, the curve is increasing. Then from -1 to 3, the curve is decreasing. Then from 3 to 4, the curve is increasing again. What is that telling us? Remember, what that means is, if the curve is increasing, the derivative, f prime of x, is positive. If the curve is decreasing, f prime of x is negative. And if the curve is increasing again, f prime of x is again positive. So that means in drawing the curve and drawing the derivative, I must start by having the derivative being positive, then switching to negative, then switching back to positive. Now, if we assume that the derivative is a continuous function, nice and smooth, then we might have something like this. There's a possible graph of the derivative function in blue. Notice how it's positive over the interval from -2 to -1, then switches to negative from -1 to 3, then switches back to positive from 3 to 4. And that's all that we have evidence for. Notice how at the stationary points, right, stationary points on the curve, the derivative is 0. Why don't you try this one on your own? Here's a graph of a function. Try to draw the graph of its derivative using a similar technique as in the previous exercise. Now would be a good time to pause. Alright, so like I did for the previous exercise, I'm going to try and find first the stationary points. So it looks like I've got a stationary point when x is -2, when x is 0, and when x is 2. That means for the derivative, and again I'll draw the derivative in blue, that means for the derivative is going to be 0 at -2, 0 at 0, and 0 at 2. All right, let's look over the first interval. First interval, increasing. Second interval, from -2 to 0, decreasing. Then from 0 to 2, decreasing again. And then from 2 on, again, increasing. All right, again, what does this mean? If the function is increasing, its derivative is positive. If the function is decreasing, its derivative is negative. In the third interval, the derivative is negative. And in the last interval, the derivative is positive. All right, so let's just draw something that passes through the zeros and meets those other conditions. All right, so the derivative in blue is positive. Negative. Now, it hits 0, but now in the third interval, the derivative is again negative. So maybe it does something like this now. And then positive. So here's a possible graph of the derivative curve for that function. I say positive because I'm not worried, I'm not really being too careful with the scale. I'm not looking at the specific slopes at the points and figuring out, calculating the slopes at the points. I'm just giving an overall general impression of the shape of the curve. Here's a third example. Maybe you recognize this curve. All right, but why don't you take a moment and try and draw the slope of its derivative. All right, so again, I'll focus first on the stationary points. It looks like we've got several. From what I see here, I see 4 stationary points. Here's one. All right, so again, I'm drawing the derivative in blue. There's a stationary point. There's a stationary point at about -1.5. a stationary point at a positive 1.5 roughly, and another stationary point here between 4 and 5. All right, now let's see. Over the first interval, the curve was increasing, derivative positive. Then the curve was decreasing, derivative negative. Then increasing, derivative positive, decreasing, derivative negative, increasing, derivative positive. So maybe it looks like this. Now, I hope you recognized a couple things here. Did you recognize the function f of x? Hopefully you recognized f of x as the sine function. Now that we've drawn f prime of x, do you recognize f prime of x? It's drawn poorly due to my tablet here, but it sure looks like the cosine function, doesn't it? And that's not a coincidence. We'll learn later on in the course that the derivative of the sine function is in fact the cosine function, and we'll prove that to be true. But now we're just going off this graphical evidence, and it seems reasonable. All right, here again we have the graph of a function. Use it to graph the derivative, f prime of x. And here we have the lower half of a semicircle. All right, why don't you pause and try this one out on your own. All right, so this one has some interesting features. We see a stationary point here when x is 0, so we would draw a 0 for the derivative. Again, I'm going to draw the derivative in blue. But now over on the edges, we have something interesting happening, right? When x gets near negative 4, or when x gets close to positive 4, something interesting happens here. If we think of the tangent lines as we get close to those values, if we were to try to draw a tangent line, what would happen if we try to draw it near x equals 4? Near x equals 4, what's happening? If I try to draw this tangent line, I get a fairly large number. And then if I get closer, I get I get that tangent line. That's a pretty large positive slope. And then if I get closer, a pretty large positive slope, and even larger, right? And so what's happening here is, as I get closer and closer to 4, my slopes are getting larger and larger, and in fact they're growing without bound. They become very large numbers. And something similar happens over here on the left. When I get close to negative 4, I'm getting very large slopes. They would be negative in this case, right? If I was to draw the tangent line here, I'd have a negative slope. And so what's happening is, if we sort of think about it, okay, I've got a decreasing, right? Decrease, and then an increase. But as I get close to the boundaries, as I get close to negative 4 and positive 4, the slopes are becoming very large negative numbers or positive numbers, respectively. And so what I get is something like this. I get vertical asymptotes near negative 4 and positive 4, and I get a graph that does something like this. All right, that has these vertical asymptotic features. That's a tricky one. Strange things happen to the derivative if the function turns vertical. And so if the function turns vertical, which is what's happening here, if we think about what's happening near the endpoints of this curve, right? If we think about what's happening near x equals 4 or x equals negative 4, the function is becoming vertical near this point. And if you remember back from algebra, the slope of a vertical line is undefined. And as we approach that undefined expression, we're taking a small x, right? We're taking and dividing it by, we're taking a change in x. And that change in x is becoming very small. And the change in y is a standard number. We're dividing by a very small number. It becomes a very large number in the end. All right, and so what happens is, as the function is becoming vertical, its derivative becomes a vertical asymptote. All right, let's do one more of these. All right, so now would be a good time to pause and try this one out on your own. All right, let's see. We have again, I'll draw the derivative in blue, and I see that I have a stationary point at x equals 3. I'm sorry, at x equals 0 and y equals 3. So let me draw my stationary point here as a 0 for the derivative. All right, then what's happening? We have an increasing over the first interval. All right, increasing. And then decreasing. All right, so I know the derivative must be positive and then negative. But then something else interesting happens. Over to the left, I see this piece right here, and I see it's a horizontal asymptote, and it looks like it's almost horizontal, right? It's getting close to horizontal, and if we think about how horizontal lines work, well, that means that the slope should be approaching 0. And something similar happens over here on the right, right? So I have an increasing function. That means that the slope, the derivative, must be positive. Over the first interval, the derivative must be negative over the second interval. But I know as I move further to the left or further to the right, I know it must be approaching 0. All right, so here's a possible curve. Approaching 0 far to the left, but staying positive, and then the derivatives get larger, but then they've got to go to 0 again. All right, notice here the derivatives, larger derivatives, all right, slopes are getting larger, slopes are getting larger, then slopes are getting smaller and getting back to 0. Now the slopes are negative, starting off small, and then becoming larger, and then approaching 0 again. And so here's a slope of, here's a graph of the derivative function, a possible graph of the derivative function. Okay, so that was like, what, 6 examples of drawing the graph of a derivative given the function. So now let's use these concepts that we've learned to determine where a function is increasing or decreasing. All right, so here we're asked to consider the function q of t is 6 plus 5t minus t squared, and we're asked, is the function increasing or decreasing at t equals 0 and t equals 4? Is there any t values where the function is not changing? All of these questions, is the derivative increasing or decreasing at t equals 0 and t equals 4? That's asking us, is the sign of the derivative positive or negative? Is there any t values where the function is not changing. That's where the derivative is equal to 0. So really what this is asking us is, we need to find the sine of f prime at 0. We need to find the sine of f prime of 4, f. Sorry, I called the function q. We need the sine of q prime of 0, the sine of q prime of 4. The third part, are there any t values where the function is not changing? We need to solve q prime of t equals 0. That's what this is asking. All right, so for all of this, we need to find the derivative function. So let's do that. Let's find q prime of t. All right, so q prime of t is the limit with with h approaching 0 of q of t plus h minus q of t over h. Just using the definition we've learned so far. That's all we can go with so far. So this is the limit with h approaching 0 of q of t plus h. That would be 6 plus 5 by t plus h minus t plus h squared minus q of t, and that is 6 plus 5t minus t squared all over h. All right, so q prime of t is then the limit with h approaching 0, expanding. That would give us, expanding all this would give us 6 plus 5t plus 5h minus t plus h squared. That's going to be a minus t squared, a minus 2th, and a minus h squared. And then I have a minus 6, a minus 5t, and a plus t squared, all divided by h. All right, so I combined a couple steps there. I expanded the binomial square and distributed and took care of all the distributions. Now let's look at the like terms. I've got a 6 and a minus 6. That goes to 0. A plus 5t and a minus 5t. Those go to 0. A minus t squared and a plus t squared. Those go to 0. All the remaining terms have a factor of h. Q prime of t is the limit with h approaching 0 of h times 5 minus 2t minus h over h, which is the limit with h approaching 0 of 5 minus 2t minus h. Letting h approach 0, then q prime of t, the derivative function, is 5 minus 2t. All that work, now we can actually answer the question. Is the function increasing or decreasing at t equals 0? Q prime at 0 is 5 minus 2 times 0, which is 5, which is positive, right? That's greater than 0, so q of t, not q prime, q of t is increasing at t equals 0. Q prime of 4 would be 5 minus 2 times 4. That's 5 minus 8. That's negative 3, which is certainly less than 0. So q of t is decreasing at t equals 4. Is there any t values where the function is not changing? Not changing translates to the derivative equaling 0. Let's solve 5 minus 2t equals 0. just a little bit of algebra here. Subtract the 5 divided by -2. T is 5/2. So, at t equals 5/2, q of t, the function, is not changing. All right, at that moment, when t equals 5/2, the curve is neither increasing nor decreasing. All right, so I think I'll stop the recording at this point, since we've kind of covered over the ideas of using the increasing and decreasing, using and how that translates to the derivative. And then we'll look at some more ideas in the second video. All right, so I'll see you there.